Nobel Prize in Physics 2025. The 2025 Nobel Prize in Physics has been awarded by the Royal Swedish Academy of Sciences to John Clock, Michael Devoret, and John Martinis for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Their work has paved the way for superconducting circuits that could form the backbone of practical quantum computers and sensors, marking a major milestone in quantum technology. Macroscopic quantum tunneling. The laureates extended quantum tunneling from microscopic scales to macroscopic systems, showing that large visible systems like superconducting circuits would exhibit quantum behaviors like tunneling and energy quantization. They used superconductor materials and created Josephson junction superconducting system where billions of Cooper pairs acted as a collective quantum object. When cooled to near absolute zero, they observed that the system's electrical state would tunnel through energy barriers, exhibiting abrupt transitions confirming quantum behavior over classical. Quantum computing enabled the development of superconducting qubits and paved the way for advancements in quantum sensing and simulation. Cryptography implications. Quantum computers could break encryption systems that rely on classical computation limits. Global relevance. Countries including India are investing heavily in quantum technology. India's National Quantum Computing Mission aims to develop functional quantum computers by 2031. Quantum tunneling. Quantum tunneling refers to a phenomenon where particles can pass through the barriers that, according to classical physics, would be impossible. Quantum tunneling occurs due to wave particle duality, where particles behave as both waves and particles. When encountering a barrier, the particle's wave function extends beyond it, giving a property of the particle appearing on the other side. Applications of quantum tunneling. Scanning tunneling microscope uses quantum tunneling to map surfaces at the atomic level. Flash memory found in USB drives and SSDs. Data is stored in floating gate transistors where electrons tunnel onto or off the gate. Josephson junctions made of two superconductors separated by a thin insulator. Electrons tunnel across the barrier, creating a precise current voltage relationship. Josephson junctions are used in superconducting quantum computers and superconducting quantum interference devices for ultra sensitive measurements. Quantum computing. Quantum tunneling enables qubits to exist in multiple states and transition between them, essential for quantum algorithms that outperform classical computers in specific tasks. Nuclear fusion. In stars and experimental reactors, tunneling allows atomic nuclei to overcome repulsive force and fuse. This process powers the sun and holds potential for limitless clean energy. Understanding quantum tunneling. Imagine rolling a ball up a hill. In classical physics, the ball lacks enough energy, it rolls back, and it cannot cross the hill. In quantum physics, due to the wave-like behavior of particles, there is small probability that the ball appears on the other side of the hill, even without having enough energy to climb over it, as if it had a tunnel through the barrier. This phenomenon is known as quantum tunneling. In quantum mechanics, particles like electrons act both as particles and waves. When a wave hits a barrier, part of it can leak through the barrier is thin or low enough. This creates a probability that the particle will be found on the other side without ever climbing over the barrier. John Clock, Michael Devoret, and John Martinis are known for discovering macroscopic quantum mechanical tunneling and energy conservation in electric circuits.